Hi, this video is about how we measure work in physics. Now, if you remember, work is a quantity in physics that's very important, and it describes a force acting on an object and that object moving a certain distance while you exert a force on it. So right now, I'm not doing any work on this dumbbell, but when I move it, I do work on it. So let's look at an example involving this dumbbell. Let's say it takes 20 newtons of force to lift this dumbbell a distance of half a meter. All right, this isn't quite half a meter, but maybe it is. But let's say it takes a force of 20 newtons to do that. How much work do I do when I lift that dumbbell half a meter? So using the work equation, force times distance, we have 20 newtons of force multiplied by half of a meter, so 0.5 meters. Multiply the numbers together, you get 10. Multiply the units together, newtons times meters, we get this unit that we can call Newton meters. But a new unit is used to replace Newton meter, and it's a unit that's named after a physicist named James Joule, and the unit for work is a joule. So joule is represented with a capital J, so I can replace this Newton meter and instead say it takes 10 joules of work to lift this dumbbell half a meter. So a joule is a joule is about how much work it takes to lift an apple above your head, to give you an idea. So 1 joule, it's not very much work. It's pretty easy to lift up an apple over your head. So 1 joule of work, not much work. Let's look at another example. Let's say a hockey puck hits a rough patch of ice, which exerts a frictional force on the hockey puck of 24 newtons over a distance of 4.0 meters. How much work is done by friction in this example? So I've drawn a quick picture over here showing a hockey puck moving to the right, and it's slowing down due to friction. So nothing else is pushing on the hockey puck to the left or right. It's just friction slowing it down, so it's kind of sliding to a stop. So how much work is done on the hockey puck by friction? Well, the force of friction is 24 newtons, and the distance that the friction is being applied on the hockey puck is 4 meters. 24 times 4 is 96, and this is 96 joules of work done on the hockey puck. Now, you might have noticed that something's a little bit different in this example. The rough patch of ice does 96 joules of work on the hockey puck. That's how we kind of say that. But this work done has a different kind of effect than the previous example where I was lifting the dumbbell. There's a different kind of effect happening here when friction is being applied to the hockey puck. And this brings us to the concept of negative work. And I want to warn you, this is potentially very confusing. So stay tuned and pay close attention to the wording on this whiteboard here. Work is negative when the force opposes the motion of the object or the system. So like the hockey puck, the force opposes the motion of the hockey puck, meaning it's in the opposite direction. There's a force pushing against the moving object, which is moving the other way. So in this case, positive or negative does not indicate the direction of the work, but rather the kind of effect that the work has on the system. This is very different from concepts like force and momentum, which are vector quantities. It's pretty simple what positive and negative mean in those cases. It just means which direction the force is moving or pushing in. So positive or negative is direction. But for work, it doesn't mean direction. Positive or negative doesn't have anything to do with the direction that the force is acting or the work is working. Rather, it's the kind of effect. Now, without getting into too many details at this point, positive work just means that something is being added to the system, like you're adding speed or height to the object. Whereas negative work is removing something from the system. There's more to it than that, and we'll see that later on as these videos continue. But for now, we can just say positive work generally adds something, and negative work generally removes something from the system. And all it is based on whether or not the force is going with the object or opposed to the object. If it's opposed, the work is negative. If the force is going with the object, then the work is positive. So, one last example here with some force diagram, free body diagram here. Let's say I've got a flat surface here, and I've got a toy sloth, and I pull this toy sloth across the flat surface at a constant speed. That wasn't very constant. Let me try again. So pull them at a constant speed across the flat surface. Now, if that's what happens, it's a rough surface, that implies that there's some friction involved. So I've drawn a free body diagram to represent the forces present on the sloth in this scenario. So I have an applied force to the right. The sloth is moving to the right. I have a frictional force acting against the motion to the left. The sloth has some gravitational force acting on it, pulling it down, but the surface that the sloth was on has a normal force pushing up, and so it balances out the gravitational force. The question here I have is, which forces do work on the sloth? We have 4 forces acting on the sloth. They all have some kind of force on it, but not all of them are actually doing work on the sloth. Remember, work is only done when 1, the object moves, check, the object is moving here, and 2, the force acting on the object is parallel to the object's velocity. The object is moving to the right in this example, and so there are only 2 forces that are actually parallel to the object's velocity, and that is 1, the applied force to the right, and the frictional force to the left. And so these are the 2 forces that are actually doing work on the sloth. The applied force is doing positive work, and the frictional force is doing negative work. Friction always is going to be doing negative work in these examples. The normal force and the gravitational force, they are perpendicular to the actual motion of the sloth. And so, by definition, they do not do any work on the sloth. So, that's all I've got for you in this video. Remember, habit is the battleground of character.